So, hi everyone, I'm Agoston, and I would like to tell a few words about who I am. Artist and educator based in Budapest, and I mainly do algorithmic art and generative art using different techniques like older plotter machines and more recent digital tools. And a part of this artistic practice, I also teach at the University of Nagy Design and Arts Institute, where we are dealing with interaction design and interactive technologies. In this talk, I would like to introduce some of my recent experiments with a new field for me. So I am really just studying these sort of possibilities and investigating. I am not a scientist, I'm an artist, and I'm just really would like to find out new ways of finding interesting patterns and interesting relationships. So the context of this is like, since a while, it will be a little bit philosophical, not that tech heavy, so I just would like to introduce the context on why I am doing this, or what is interesting for me in working with quantum. Digital culture and the mediated environment have long played the role of a kind of second nature in human society, as we can all feel and perceive. In recent decades, there are some shift in transcending classical dualism, as I call, and I will get back to that later. So the binary systems, the digital zeros and ones, and the yes-no world of dualism is changing into something different, where we are even not sure about the consensus on objective reality. You can see in the news, you can see everywhere what's happening. It's very, it's not a yes-no situation, but it's very complex. So from an artistic point of view and a philosophical perspective, the recent achievements of quantum computation are reopening core ontological levels of experience, because these are a little bit different than what we are used to. So I would like to start with, I will show 3 experiments to you that I'm working on and I made. The first one is about randomness. As we all know, we are using pseudo-random number generators with computers, so these are not real random numbers, but we are faking randomness with our computers. But there are also real random number generators like the weather, or like different natural processes that we can use as random number generators. Also, scientists consider quantum random number generation as true random, because we cannot predict, it's not deterministic how the randomness will turn out from when we are measuring a quantum system. So this is my first hello world application of quantum computing. You can see here on the left there is a series of binary numbers, which is a minus and a plus, zeros and ones. It's like a random generated series of binary numbers. And on the right, you can see the quantum circuit that I've made it with. I am not really involved deeply in quantum algorithms, so this is very basic that I can share with you today. It's one of the most simplest circuits that you can see here. We have 1 qubit, which is like we don't know where the qubit position is when we are placing it in superposition, and we measure this qubit at a certain time. So when we measure the system will collapse, and as a result, we will get a 0 or a 1. But before we measure, we don't know in which state is the qubit is, until we measure, then we collapse the system, and it will turn out as a 0 or a 1. And you can see this circuit which is generated the random number series on the left that you can see. So I am using a Python-based library called Qiskit for quantum computing. It's provided by IBM. And what is good with it is that you are not only simulating the quantum system, but you can also run your code on quantum computers. So if you propose a request to IBM, you send your circuit up to the quantum computer, you can get back the result. So what you see here, these are running on real quantum computers, and this is why it's philosophically or metaphysically it's interesting for me, that it's really using real random numbers. So the other part, a part of entanglement, you can see I'm referring to rituals here, because I find it really interesting to combine ancient technologies and philosophical systems to current computational culture. So from time to time, also with my students, but also with my artistic practice, I like to use deep media related tools and structures. So sometimes I'm using stick charts for navigational systems, different tools, but for these experiments I am referring to the Yiking, which is a divination system. You might be familiar, it's one of the first binary systems actually. So a Yiking is a symbolic system from the ancient China where they were trying to predict the future, so predict if a decision is bad or good. They were using this as a divination system, so continuous lines are equal to 1 and broken lines are equal to 0. So if you, I don't know how clear it is, but if I zoom in, you can see that these shapes are continuous or broken. So this is a binary system used for divination, and it has a ritual procedure how they were trying to, even today it's well used everywhere to predict the future. So I find this beautiful, this system, and I find beautiful these sort of languages, these graphical notation systems that are used and functional. So it's not only just for the patterns, but it has an interesting function. And I was using the Yiking system and just build on the previous example I showed to you. I was creating Yiking hexagrams, which are 6 lines of Yiking zeros or ones, and generating a series of Yiking hexagrams with quantum circuits. So here you can see that these hexagrams are symmetrical, so the top 3 is equal to the bottom 3, and this is made through entanglement, which means that you can connect 2 qubits and they will have the same state when you measure them, regardless of where they are. So if they are far apart in anywhere else, and you measure one of them, the other one, which is in entanglement with this qubit, will be the same. So I'm doing here this entanglement. The first qubit is entangled with the 4th one, the second is entangled with the 5th one, and the third is entangled with the 6th. So these are the symmetrical Yiking. You can see on the circuit, this is like illustrating that the first 3 qubits are entangled with the second 3 qubits. So as a result, each of those should be symmetrical, like 111, 111, for example, but as you can see that there are not all of them symmetrical, which is highlighted with these blue-black lines, because there is quantum noise in the system, so it's not perfect. Today's quantum computers are unstable, and it's really hard to make them precise. So here I'm investigating the limits of the current state of a quantum computer. So you can see the errors there, or what we can call quantum noise. I also made a small sonification for this experiment. I think this has some sound, but it's very, very minimal sound. But I don't know if we have the sound. Yeah, no, yes. This is noise. So usually the visualizations that I do and the sonification is made with JavaScript and web-based technologies. So The way I'm doing these experiments is I'm getting the result from the computer, the quantum computer, as a result of zeros and ones, and I'm visualizing in the browser. So basically these are browser-based experiments. And it's like very minimalistic. I just would like to find some aesthetic possibilities how I can sonify these strange, constellations and strange algorithms. So it's very minimal. And another algorithm I would like to show here, we can call the quantum walk algorithm, which is like, if you know the random walk, the classical random walk algorithm is like flipping coins. So if someone is flipping a coin, it will get a 0 or a 1 as a result. And if you flip another one, you can get a second one. So, and you can walk based on the results of these zeros or ones. So quantum walk algorithm is very common, and the classical random walk algorithm is very common, and it's used in very many cases for music making, for simulating very simple scenarios. And there is a difference if you generate this with quantum, because it's the system that was predictable becomes a probability-based system. So here you can see that I am using 12 qubits for these experiments, and all of them I put in superposition, which means I don't know if they are in ones or zeros. And then I measure the system, so they will fall either into ones or zeros. And on the left, you can see in the first line how they fell into 1 or 0. With the white is the 1 and the black is the 0. So it's a binary array visualization. And if you go to the bottom, you can see the probability of that specific cell, how probable that the qubit will fall into that position. So this is why this is a probability field that you can see here on the top, which is the result of the actual measurement. And if you go to the bottom, you will see how probable is that the qubit will fall into at that position from the 12 steps, the steps of the walk, into 1 or 0. So at the end you can see it's very noisy, and on the left there are the initial steps. These are much more have much more difference. So it's really an interesting pattern that turns out when you try to map the probability field of these steps of this quantum walk. The code itself is very simple, so you can see that I'm just defining how much steps I want to use and how much qubits, and how much, and when I measure them and how I want to visualize. So this is the third experiment, which is a little bit complex. It's hard to describe, but it's very basic. So it's really not near what you can do with a quantum computer. Actually, it's not really effective to make systems like this, because it is much easier to make with classical bits like ones and zeros and define the rule between those elements, how they should change. So the last one that I would like to show is I call conditional space. So a space that is being unfolding while we are observing it. And I usually use for these occasion cellular automata, which is like very simple structures, but I really like to use in different scenarios, also making sounds with them, but also in my visual works, which is very basic system. It's a traditional computational system. From the top to the bottom, you can see on the left, these are classical cellular automata, which means in the first line, there are a few cells. This is why we call these cellular, because these are cells near each other. and one of them is alive and one of them is dead. Which one is alive is highlighted with blue, and the dead ones are not visible. And step by step you can see there is a simple rule if this automata should stay alive or should be dead, and an emergent pattern will fold out based on the simulation. On the right, with these ones, these are similarly generated, but with a quantum computer, where I place, instead of classical dual 1-0 based bits, I using qubits, and I put the system into superposition. And you can also see, which is also called the quantum interference or the probability field, how probable that these cells should be alive or dead. So it's not a 1 and 0 threshold there anymore, but a field of probabilities. And I find it quite fascinating that you can see very strange patterns are emerging based on these probability waves. So here on the right, the system is measured at once, while on the left it's step-by-step sequence. And I can also show how it is working in animation. So on the left you can see the classical automata is step-by-step generated, and on the right I try to make a different sort of sonification and visualization for the system, which is aesthetically interesting, and it's really different from the classical step-by-step generation. I try to illustrate with this experiment how they are measured at the same time, and they get their probability values while during the measurement. So I will play it again just to, yeah, it's very short. I'm using the same rule for the automata on the left and the same rule for the automata on the right, but on the left these are classical bits on a classical computer, and on the right these are qubits in superposition measured at once on a quantum computer. And on the right you can see how the rules are implemented in Qiskit. So these are quantum gates that are connected together, and they try to mimic the behavior of a classical automata. It's super ineffective, and it's really hard. As you can see, I have very low resolution there, so I can run only maximum of 100 qubits today with these computers. In the future, it will be more interesting if we have many more qubits, but it's in a very, very immature state at the moment. But I think there are many possibilities in this direction. So if I would like to summarize what I have with these experiments as part of my ongoing artistic research in algorithmic visualizations and sonifications, I would say for me it's interesting that rather than an evolving along a single deterministic path, the system simultaneously explores a spectrum of possible configurations, each with a corresponding probability amplitude. So it's like being at more place at once. For me, it's very interesting, and it's really philosophically a challenging concept to visualize, to understand, and to even to use it in our everyday lives when we make our decisions. So we have these forking, I don't know, thought possibilities. But if we think of quantum, we are measuring from time to time and collapsing the system and see each possibilities at the same time. I think it's quite fascinating. So in the previous example, you saw the same local rules were applied, but now they act on qubits in uncertain states, which produces interference. And we are starting to witness a shift, as I said, I think from classical dualistic systems to these uncertain systems, even in society. So it's like really interesting analogy to think of quantum sensing and quantum presence. And so to summarize this non-dualist concept, because I'm also practicing Zazen and Zen meditation, I really find it interesting the mind and the mindset when it is in superposition. It's not in one or the other perspective, but it's in between. And I think there is an interesting analogy with quantum mechanics. Particles do not have definite states until observed, and quantum entanglement suggests that separated particles remain fundamentally connected beyond classical space-time constraints. I think it's quite interesting. And if you think of quantum, I would like to quote Alan Watts, who was a Zen practitioner, but also there are many analogies that can be found in those philosophies. And I think it's an interesting thought. As a matter of fact, you cannot compare this present experience with a past experience. You can only compare it with a memory of the past, which is a part of the present experience. When you see clearly that memory is a form of present experience, it will be obvious that trying to separate yourself from this experience is as impossible as trying to make your teeth bite themselves. I think I'm ran out of time already, so thank you so much for your attention.
Thank you very much for that very interesting talk. I was interested also from your paper in what you were saying about that kind of shift in non-dualism and ways of thinking about reality, and I wondered if you could say any more about why you think right at this moment that kind of paves the way for this relevance of quantum ways of thinking about things. Just a brief expansion on that.
Sorry, I didn't hear the end. What was the question?
So the moment in time, like why you're interested in this now in terms of shifting ideas about ways of thinking about reality? Mm-hmm.
It's a good question. I'm not really sure. I mean, the things are I think too complex or very complex. Everything is hyper connected, and for this, it's really hard to keep up with our focus and our mind to understand what's happening, to understand the oversaturated diversity of the news that we hear. So I take it in really on a social mind or social zeitgeist, or how to say it, like we are achieving that state when there are parallel truths are out there, and it's really hard to differentiate between what is true and what is not true. Why now? Because we have this amount of networked technologies. I think we are in a hive, and our mind is connected, so we can really think with abroad the different space and time constraints. We can communicate, real time. So meanwhile, while we are communicating real time, we are losing our connection with our with the memory from the past. It's really hard to trace back the reasons. So there are many things I think that are accumulating in this situation. And there are different ways to tackle this, to survive or to understand and to act and to make the things to live together with this situation.
Great, thank you. I'll take a couple of questions from the audience. Just bear with me.
Hi, this is lovely stuff. I can see. One of the massive problems with that people have talked about with quantum theory is mathematically quantities arise like complex numbers, which we then have difficulty mapping to reality. Now you've created some visualizations where you've made some decisions to map some of the quantities that arise from quantum simulations as visual and also as sound In the last one especially, I was quite interested, the cellular automaton one, how did you map the quantum results to sound? What rules did you use for that in this case?
Yeah, thanks for this question. I mean, it's really important part because I'm working with projects like visualizations and sonifications for different occasions, computer vision, things like that. And it's very important, the mapping itself, how you map the different areas of one domain to another domain. So here, for example, I'm always using very simple elements like sound synthesis, like sine waves and noise and filters and stuff like that. And I'm using very simple data. So actually, these are numbers between zeros or ones, or numbers of ones or zeros. It's not really complex data set. It's just, I don't know, thousands of binary numbers. And I just would like to make it tangible. So through audio, you should hear if it's continuous or discrete. So there are different sounds, short sounds, high cut sounds for discrete events, and continuous drone-like sounds for the wave-like behavior. And I find it really interesting. If we work with that amount of information and data as we work today, it's a really interesting field to map all of those informations and try to make them more understandable.
Great.
Yeah.
Thank you for that. I'm just going to read a question from the live stream from Maria Jose Rios Araya, saying, can you please explain more about the relation between quantum and random? So what is the relevance of randomness in quantum ideas?
Sorry, I didn't hear again exactly.
The relationship between quantum and random, more precisely. Randomness and quantumness and randomness.
Yeah, I mean, it's for me, it's a philosophical question more like, because I'm not a scientist, as I mentioned, but I work with chance, and I work with different probabilities from time to time when I'm doing art. So I'm building systems, and these systems behave in generative autonomous ways. So I have to work with randomness. But it's deeply rooted in our culture. Like, I don't know if you think of the 60s, like the Fluxus movement, and also live coding and the things that we all know about. We are using randomness a lot, and we are working with it every day. So we are building scenarios with our code, and it's just a funny thing to think about real randomness versus simulated randomness. So it sounds like we are simulating everything with our computers. It's not really, still not natural, but it's a simulated something. And with these quantum principles, it's just like, it's a poetic way of dealing with this issue. If it's a secondary nature, or if it's at its heart, it's natural, a process like a random process. So here, randomness has a very rich, possibilities in itself that is really good to investigate, I think.
Thanks very much.